Good morning, sir.
Very good morning, students.
Good morning, sir.
Morning,
Good
sir.
morning, sir.
Good morning, sir.
Good morning, all of you.
So,
So today we are going to discuss about the concepts of coordination chemistry or complex compounds. Okay, let us start with the discussion. If you look at things around us, students, so like leaves or our own human blood or any biological reactions, if you look at the reactions happening around us in nature, in every reaction there is a complex compound. Yes or no? So complex compounds are very high in number and they are present around us, even inside our bodies as well as in the experimental setups. So it is quite important to understand the chemistry of such complexes which we are dealing with our day-to-day lives. If you are looking at a lot of complexes in our everyday life, so it is quite important to understand their chemistry. So first we should know what are complex compounds or what are complexes, and what is the difference between a complex compound and a simple salt or a double salt. And then we will be understanding about their chemistry, how the ligands are there, how these ligands are going to be complexed with the metal ions. All that things will be studied. Right?
Yes, sir.
Just a second. Yeah, we all know what is salt, students. Simple salt. Salts are those type of compounds which contain one type of cation and only one type of anion. If a particular salt contains only one type of cation and one type of anion, then that is called as a simple salt. You all might have done the salt analysis, yes or no, in your 11th and 12th standards, where you have figured out
Yes, sir.
the type of anions and type of cations present. If only one type of cation and one type of anion there, that is simple salt. Example, NaCl, Na plus 1 cation, Cl minus 1 anion. KCN, K plus Cn minus, RbCl, Rb plus Cn minus. Okay, K plus Cn minus. One cation should be there and one anion should be there. That is the only point for a simple salt. These salts completely ionize in aqueous solution and give the test of all its constituent ions in aqueous solution. You might have studied ionic equilibrium. Yes or no? In the ionic equilibrium, you might have looked at salt hydrolysis. Yes or no? Salt hydrolysis, 4 different types salts you have seen. Salt from a weak acid and a strong base, strong acid and weak base, weak acid, weak base, strong acid, strong base. All salts are strong electrolytes. They will undergo complete dissociation. But all salts will not undergo hydrolysis. All salts are strong electrolytes. That means salts will be undergoing complete dissociation, but they will not undergo hydrolysis. But all salts will not undergo hydrolysis. So which salts will be undergoing hydrolysis? Only salt of weak acid plus weak base, strong acid plus weak base, weak acid plus a strong base. Only salts from these 3 scenarios will undergo hydrolysis. Salt of strong acid and strong base will not undergo hydrolysis. Why it will not undergo hydrolysis? We'll look at in the concepts of ionic equilibrium. There is no active ion present. Okay, these salts completely ionize in aqueous solution and give the test of all of its constituent ions. Obviously, if it completely dissociate to Na plus and Cl minus, if you do the test of Na plus, you will get a positive result. If you do the test of Cl minus, again you will get a positive result, right? This is about simple salt. What is simple salt? Only one type of cation and anion should be present. Addition salts. When 2 or more simple salts chemically combine together, I am adding 2 salts now, and they are chemically combining together in fixed proportion by weight. That means as per mole ratio they are combining. The molecular or addition compounds formed, they are said to be addition salts. What are addition salts? Addition salts are obtained by the combination of simple salts as per the mole ratios. Depending upon the behavior in the aqueous solution, the addition salts, they were actually classified into 2 types. Double salts, complex salts, or coordination compounds. What is a simple salt? Simple salt, 1 cation, 1 anion. Add a mixture of salts, like 2 or 3 salts. And if these mixture of salts are combining according to some weight ratio or mole ratio, then you get the addition salt. The addition salt can be classified as 2 types: double salts or coordination compounds. What is a double salt, students, if you remember? Double salt,
That completely dissociates on mixing with water.
very good. Coordination compounds,
That retain their identity on mixing with water.
very
They
good.
just broke into
They do
ions.
not completely dissociate. Okay. Double salts means those addition salts which, when dissolved in water, give the test of all its constituent ions. That is, complete ionization is possible for these type of salts. Complete ionization will be possible for these type of salts. Let us look at some examples. Simple salts mean only one type of cation, one type of anion. Adding simple salts, 2 or more simple salts, you get a double salt. Yes, Anushka, any doubts? Okay, fine. So the addition salts are those salts which are obtained by the addition of more than two types of salts as per the mole ratio. These addition salts can be again classified into two types: double salts or complex compounds. Double salts are those which will be completely dissociating into all types of ions whenever we add water. In water, they give that if the double salt dissociate to all types of ion, it gives the positive test for all the constituent ions. Yes or no? But if we have a complex salt, it will not dissociate into all types of ions. It gives some complex ions. So you have to remember the examples of double salts. Like I have added KCl and MgCl2. KCl plus MgCl2 gives what upon heating?
Carnellite.
Write down that. KCl.MgCl2.6H2O. This is your carnellite. Very good. KCl.MgCl2.6H2O. That is your carnellite. How is it obtained? It is obtained by adding KCl and MgCl2 and heating it. Yes or no? As per the mole ratio, the combination has been done. Now we are adding to water, making this particular carnellite dissolve. So it gives K plus ion. So KCl gives what? K plus and Cl minus. MgCl2 gives what? Mg plus 2 and 2Cl minus. That means what type of ions are there? We have K plus ion, we have Mg plus 2 ion, we have 3 chloride ions. That means when you treat KCl.MgCl2.SH2O with water, you are getting all types of ions. That means if I do the test of all these ions, like from the salt analysis, if I do the test for K plus, Mg plus 2, Cl minus, for all the three, I am going to get a positive result. What do you mean by that? What do you mean by that? Indirectly, if I am getting the positive for K plus, Mg plus 2, Cl minus, can I say this particular carnellite is undergoing complete dissociation? Indirectly, because if we don't know whether carnellite will undergo complete dissociation or not, what we can do instead? In carnellite, we know that K plus, Mg plus 2 chloride ions are there. I will test for all those ions in that particular carnellite salt solution. If I am getting positive results for all these ions, then I can say carnellite undergone complete dissociation. Is that clear, students? Yes or no?
Yes, sir.
Yes, sir.
Very good. Simple logic. So if I say complete dissociation happens, that automatically means these ions giving positive results, or indirectly, if these ions are giving positive results, I can say complete dissociation occurs. So next example of double salts. More salt, FeSO4 ferrous sulfate, ammonium sulfate. Whenever you add these two and do the crystallization, you are going to generate a more salts. FeSO4.NH4 taken twice SO4.6H2O. When you add this more salt to water, you will again get Fe plus 2. Like FeSO4 dissociates to give what? FeSO4 alone. Fe plus 2 plus SO4 minus 2. Ammonium sulfate again dissociates to give NH4 plus 2 and SO4 2 minus. That means we have what type of ions? Fe plus 2, SO4 2 minus, Fe plus 2 ion, sulfate ion, ammonium ion. So if you are getting a positive result for all these three ions, that means the more salt is undergoing complete dissociation. So more salt can be categorized as a double salt. More salt can be categorized as a double salt, right? Yes, FeSO4.NH4 taken to SO4.6H2O, that is a more salt which will undergo complete dissociation again. Next example, potash alum. Write down these examples are important. Which of the following can be double salts? Like that questions can also become. K2SO4 plus Al2SO4 taken thrice. Potassium sulfate, aluminum sulfate we have added. We have done the crystallization. Generated a salt. K2SO4.Al2SO4 taken thrice dot 24H2O. And this salt again in the presence of water, it gives the K plus ion, Al plus 3 ion and SO4 minus 2 ion. These type of ions are obtained. Of course, 2K plus, 2Al plus 3, 4 SO4 2 minus ions are there. So since these ions are obtained, we get the positive result for these ions. So potash alum is going to be your respective double salts. Can anyone say What is the N factor of potash alum? These are all salts, no? For salts, how we can calculate the N factor?
Sir, 6.
Total positive or total negative charge.
Yes, very good. What is that? Total magnitude of positive charge or negative charge. What is that magnitude here?
8.
8.
8. Very good. Total magnitude of positive or negative charge. So here we have 2K plus and 2Al plus 3. So 2K plus 2, 2Al plus 3 plus 6 plus 2 plus 6 plus 8. So magnitude is 8. Similarly, negative charges also should be same magnitude, but just with the opposite sign, because salt is as a whole, it is neutral, right? We cannot have more positive charge and less negative charge. Okay, like that, whenever these double salts were given to you, either in the molarity calculations or in the equivalent weight calculations, you can use this formula as well. Then comes the complex salt, simple salts combined in a different ratio to get addition salts. Addition salts can be double salts as well as complex salts. Complex salts means what? They are not going to give complete all types of ions. That means they will not dissociate to give all types of ions. Yes, these compounds do not completely dissociate. Prachi, note down. Mode salt is FeSO4 dot NH4 taken twice SO4 dot 6H2O. Okay, and let me know if you're done. Double salts are those salts which will not dissociate to give all types of ions. Okay, done. Very good. Complex salt. These compounds do not completely dissociate into constituent ions in aqueous solution. Means they do not give the test of all their constituent ions. Example, let us take. I have told you in the D block also, if you remember, when we add KCN with the FeCN taken twice, which is obtained from FeCl2, we are generating K4 FeCN6. If you remember, we have also discussed about the hybridization of this metal ion in the complex. What is the hybridization? We have checked for two possibilities, like the inner 3D orbitals can involve in the hybridization, or the outermost 4D orbitals, they can also involve in the hybridization. Okay, you don't need to worry with that part, we'll discuss again. But K4 FeCN6, if you look at the dissociation, what it will happen? It will dissociate to give, like if we have AXBY, how it dissociates? We get a XA, A will be having a Y plus ions, and we'll have YB, and B should be having the X minus. That means
4K
AX,
plus.
yeah,
4K plus and
AXBY
FeC.
dissociates to give XAY plus plus YBX minus. Similarly, here you get 4K plus FeCN6 whole minus 4. The charge of this complex ion should be equal to the number of K plus ions. If you look at this dissociation, students, what we are getting actually? Already the dissociation mentioned here, so we don't need to worry at all. So in the presence of H2O, it dissociates to give 4K plus and FeCN6 whole 4 minus. If you look at this dissociation, can I say, although we have cyanide ions, initially we have KCN, so K plus Cn minus, FeCN2, Fe plus 2, Cn minus, 2Cn minus, of course. Initially, I have what type of ions? K plus ion is there, Cn minus ion is there, and Fe plus 2 ions are there. But after we generate the complex is giving only K plus ions and FeCN6 whole 4 minus ion. That means if I do the test of all the ions like K plus Cn minus Fe plus 2, which I am going to get positive result?
Only for K plus.
Only for K plus I will be getting a positive result. Very good. What about Cn minus and Fe plus 2? Cn minus and Fe plus 2, they are not present as a individual ions. they are present as a complex ion. So you will not be getting positive result for Fe plus 2 or Cn minus. Fe plus 2 and Cn minus, you will not get a positive result. Fe plus 2 or Cn minus, no positive results. Understood now? Can I proceed further?
Yes, sir.
Yes, very good. So K plus you will get positive ion, Fe plus 2 Cn minus you will not get a positive ion. You will not get a positive test. So K4 FeCN6, they have already mentioned the name here, potassium ferrocyanate, but we will discuss how to name complex compounds in the upcoming sessions. K4 FeCN6 dissociates to give 4K plus and FeCN6 4 minus. The K plus ions will be showing positive test because they are present as individual ions, whereas Fe plus 2 and Cn minus you will not have a positive test. So our role in complexes will be mainly about understanding how this complex is formed and what type of forces are present between the Fe plus 2 and Cn minus and how are they governing. Okay? Yeah, look at this scenario. In the formation of complex, like if you take K4 FeCN6, what it is dissociating? We are getting 4K plus and FeCN6 whole 4 minus. What is the oxidation state of metal ion? Calculate that. K4 FeCN6, FeCN6 4 minus ion is there. Let us say oxidation state of iron is X. Cyanide is in which oxidation state? -1 state.
Plus
So
2.
yeah, 1 into X plus 6 into -1. The total charge of complex ion is -4. So X should be in the +2 state. So iron is in which state? Fe is in +2 state. It is now forming bonds with the cyanide, Cn minus. How many? 6 cyanides. So cyanides are coming and they are forming some bond with your Fe plus 2. I'm not specifying what type of bond is formed. Of course, a coordinate covalent bond is formed. So this is how you are going to have. The cyanide ion is actually giving the electrons to the empty d orbitals of a metal. I have told you about acception and attraction. Fe plus 2 being positively charged, it will obviously attract electrons because electrons are negative charge. Fe plus 2 is positively charged, positive attracts negative. That is true. But whether it will accept electrons or not, that depends upon availability of vacant orbitals. Acception and attraction is different. Fe plus 2 will accept the electrons also. It not only attracts. Why? Because Fe plus 2 has vacant orbitals. So Fe plus 2, write down the electronic configuration of iron Fe. Argon, 4s2, 3d6.
3d6.
Very good. Fe plus 2. Argon,
3d6 4s0.
3d6. Very good. This is 3d. This is 4s. After 4s, what do we have?
4p.
4p. Understand this very carefully, students. Yes or no? This is 3d, 4s, 4p, and 4d. 3d6 electronic configuration you write down. 3d6 means first you should follow the Hund's rule. Each d orbital should be getting 1 electron. Then you should start the pairing. The sixth electron has been paired in the one of the d orbital. So we are having electrons from 6 cyanides. The same example I have explained in the D block also. 6 each cyanide ion, okay, each Cn minus, each cyanide ion is providing 2 electrons because you have a coordinate bond. Cyanide ion is the ligand. Ligand is electron donor. So cyanide ion is providing the electrons. Each Cn minus is providing 2 electrons. So 6 Cn minus will provide 12 electrons. Each d orbital can have a maximum of 6 electrons. Sorry, 2 electrons. Each d orbital, any d orbital can have a maximum of 2 electrons. So to accommodate, how many electrons are there? To accommodate 12 electrons, we need 6 vacant d orbitals. Understood this point or not, students? Fe plus 2 is forming coordinate bonds with cyanide. How many cyanide? 6 cyanide. Each cyanide is giving how many electrons? 2 electrons. How many cyanides are there? 6 cyanides. So total number of electrons given how many? 6 into 2. 12 electrons. We know every d orbital, every vacant d orbital can occupy a maximum of 2 electrons only. We are getting 12 electrons from 6 cyanides. So how many d orbitals we should require? 6 vacant d orbitals should be required.
6.
Yes or no? Yes, very good. What are those 6 vacant d orbitals? You can have one possibility. You can have 1 4s. You can have 3 4p. You can have 2 4d. 2 4d. Yes or no? Because in the 4s subshell, we have only one atomic orbital, that is 4s atomic orbital. In the 4p, you have 4px, 4py, 4pz. So 3 4p atomic orbitals. In the 4d, you have 5d orbitals. Out of those 5, we have taken 2. So 1 4s, 3 4p, 2 4d. 1 plus 3 plus 2. How many? 6. So I can choose this set or not? I can choose this set. One possibility. What is the other set I can choose?
Inner D2sp3.
Yes, very good. I can have 2 3d, 1 4s, and 3 4p. Why is this set happening? This set will also happen. Why? Because we can have the Fe plus 2 electronic configuration as argon. Because cyanides are coming and donating their electrons, the inner d electrons of the Fe plus 2, that is metal ion, since cyanides are coming, right? Because cyanides are coming means electron repulsions are increasing. Cyanides are donating the electrons. Electron repulsions are increasing. So in the d orbital, we have, in the inner d orbitals of Fe plus 2, we have electrons. These electrons can repel with the electrons of cyanide. To minimize repulsions, they can pair up. How they can pair up? They can pair up in such a way such that now you have 6 electrons only present in the 3 orbitals. And you have 4s as it is, 4p as it is, 4d also as it is. Now we need 6 vacant d orbitals. What are those? 2 3d, the second set. 1 4s and 3 4p. So these are the two possibilities. If first one is the possibility, like we have 1 4s, 3 4p, and 2 4d, what is the hybridization? Yes, p3 d2. What is the hybridization in the second possibility? 2 3d, 1 4s, 3 4p. Yes, what is the hybridization?
D2sp3.
D2 sp3.
D2sp3.
Now how we will decide? That is the point. How we can say that whether the ligand is going to make the inner electrons pair up, or whether the ligand will just place their electrons in the outermost orbitals. How we can say that, students?
By analyzing their donating capabilities and
Yeah, how
their
do we do that? That's what I'm asking.
spectrochemical series has told
Very
us.
good. Spectrochemical series talks about ligand strength. If the ligand is a strong ligand, then it will repel the inner electrons greatly. Because of that, the pairing will happen. This is a scenario in the strong ligand. What type of ligand is a CN minus?
Strong ligand.
Strong ligand. Yes or no? CN minus is strong
Strong
ligand.
ligand.
Very good. So for CN minus, since it is a strong ligand, what type of possibility is happening? sp3d2 or d2sp3?
D2sp3.
D2sp3.
D2
Now I'll
SP3.
yes, very good. This is a correct possibility. We look at whether Cn minus is a strong ligand, what are the set of strong ligands. All these we are going to look at. This is the same concept we again discuss in valence bond theory. Not only for K4 Fe6, for every species we are going to write. Now I'll ask one simple question. Sir, you are only saying Cn minus are having experiencing repulsions with 3D. If Cn minus is experiencing repulsions with 3D, why can't Cn minus just repel these inner d electrons? Cn minus is coming, right? It can repel these inner d electrons and make them pair. And why can't they simply leave these two electrons and start pairing from 4s, 4p, 4d? Because repulsions are high now. Cn minus, why are they making the pairing happening in the 3D? And again they are going into 3D. Why can't they leave the 3D empty and go to 4s, 4p, 4d?
Due to high energy difference between 3D and 4D.
High. So first point is you cannot leave lower atomic orbitals empty and fill your electrons in the higher atomic orbitals. Yes or no? The electronic repulsion would be always there. Remember, the electronic repulsion would be always there. But because of these repulsions, you cannot emptily leave some of the inner or lower energy orbitals and go filling in the higher energy orbitals. You cannot leave an orbital empty and fill in the higher energy level. That's why you cannot leave 3D empty. That's why you're going to have D2sp3 as a hybridization. Okay, fine, students. This is your simple analysis of how the complex is going to be forming or how the metal ion is going to be forming a coordinate bond with the ligand to form a respective complex. So ligand will form the coordinate bond with the metal ion. In the process of coordinate bond formation, the ligand is providing two electrons. So which is electron pair donor? Donor. Ligand, right? Electron pair donor is the ligand. What is electron pair acceptor here? Which is accepting the electrons?
Metal ion.
Metal ion. So that is your electron pair acceptor. So electron pair acceptor is the metal ion, especially called as central metal ion. Electron pair donor is the ligand. In the process of donation electrons, the ligand will form a coordinate bond. Based on the number of ligands, the structure of the complex formed that is going to be decided. Based on the number of ligands, the structure of the complex formed that is going to be decided. Is everything clear so far, students? Yes or no?
Yes,
Yes,
sir.
sir.
Yes, very good. So we need to understand few terms in the coordination compounds. What are those terms? Central metal atom or ion. Like just now in the previous example, Fe+2 is a central metal ion. Ligand is electron pair donor. Coordination number. Coordination number means
Number of ligands surrounding the central metal ion.
is that true, Faizan, for all the cases?
No, sir, not for all the cases because we have many types of ligands like more
So what is
dentate
the
by
generalized formula then, which is true for all the cases?
number
Can I
of electron pair accepted.
number of coordinate bonds, you can say like that?
Yes, sir.
Yes. Coordination number is equals to the number of ligands surrounding the central metal ion in case of monodentate ligands. Monodentate means only one bond is formed. In case of bidentate, it will be 2 into number of ligands. But bidentate ligand means each ligand will form 2 bonds, no? So what you can say especially is number of coordinate bonds formed. Coordination sphere. So coordination sphere is wherever we have the complex entity. In the complex, we have some counter ions and the complex ion, which is present in square bracket especially. That is nothing but a coordination sphere. So we'll look at now each and everything. Terminology used in coordination compounds. K4 Fe6. What is this? Fe6. This is nothing but your coordination sphere because that is leading to complex ion. K plus ions. What are these ions? 4 K plus ions. We are having K4 Fe6. We are giving 4K plus ion. This compound upon dissociation gives 4K plus and Fe6 minus 4. 4K plus ions, that is the K plus ions are surrounding the complex ion. So they are making the charge of the complex ion nullified. So they are acting as a counter ions. What are this called as counter ion? What about Fe? Fe is the central metal ion. What about Cn? Cn is the ligand. What about the 6 there? What about the 6? 6 is nothing but the number of,
Number of ligands.
number of ligands. Yes or no? Which is equal to your
Coordination.
coordination number in this particular case, because Cn minus is a monodentate ligand. Number of ligands is equals to 6. Coordination number is equal to 6. Only true in case of monodentate. Monodentate. Monodentate means only one coordinate bond is formed. If you have more than one coordinate bond formation, if you have a bidentate, tridentate, then the coordination number is equals to number of coordinate bonds. All of you note it down, students. All of you note it down. Note down and let me know. Okay, fine. Central metal atom or ion? The metal ion which form complex ion in combination with anions, cations or neutral molecules, that is called as your central metal ion. The metal ion which is forming complex in combination with anions, cations or neutral molecules. You may ask a question. Sir, you are saying that anions are giving the electrons to metal ion. That's fine. I can agree with that. Mn plus is there. Anion is negatively charged or positively charged? Anion is negatively charged, right? Yes or no? So anions, so there is a ligand which is negatively charged. So if the negatively charged ligand is there, it can donate the electrons. So we can agree with that point. We can agree with that point. With the neutral molecules also, I can agree. So neutral molecules can also donate their lone pair. But how are you saying the cations can donate the electron pairs? Cations already has positive charge. From in the cations which are possessing positive charge also, there is a possibility of presence of lone pair of electrons. There are some cationic ligands also. Right on that point. Along with the anions, along with the anions and neutral molecules, cations can also behave as ligands. Cations can also behave as ligands, as they can donate their lone pair of electrons. Can I say ammonium ion is a ligand or not?
Yes, sir.
Sure.
Ammonia, not ammonia. I think ammonium, yes, sir.
Ammonium, not ammonia, ammonium ion.
NH4 plus, no, sir.
Yeah. Ligand or not?
No,
Yes.
sir.
So if you look at ammonium ion formation, how is it formed? Whenever ammonia is treated with H plus. Yes or no? In ammonia, we have 3 NH bonds and we have a lone pair of electrons on nitrogen. The lone pair of electrons on nitrogen, they were attacking the positively charged H plus ion from some acid. Lone pair of electrons on nitrogen, whenever they attack H plus, what they are going to be forming? Nitrogen will now form a new bond with hydrogen. Since only nitrogen is donating the electrons, it is acting as a donor atom. H plus is a accepting electrons, so hydrogen acts as a acceptor. So coordinate bond is formed. Nitrogen already has 3 NH bonds as it is, and in total NH4 will be having a plus charge. So in the ammonium ion, do we have a lone pair of electron on any atom? No.
No, sir.
So although it is a positively charged species, we cannot say that every positively charged species can be acting as a ligand. For a positively charged species to act as a ligand, its central metal atom should contain at least one lone pair of electron, which is not available in ammonia. So ammonium cannot act as ligand. Cannot act as a ligand. Understood now? Central metal ion acts as an electron pair acceptor and form coordinate bonds because it is accepting the electron from the ligand. So that is accepting an electron and it is forming a coordinate bonds with a donor species. Example, FeCN6 whole 4 minus, the cyanides are providing the electrons to Fe plus 2. So coordinate bonds are going to be formed between cyanide and Fe plus 2. This is about your basic introduction of central metal ion. Ligands, then comes ligands. Note down if you want to note it down. You can take a short notes. Okay, fine. Then comes ligand, students. The anions, cations are neutral molecules which combine with central metal ion to form complex ion. They are called as ligands. They act as electron pair donors, Lewis bases, which donate electron pair to the central metal ion and form coordinate bonds. They act as electron pair donors, which donate electron pair to central metal ion and form coordinate bonds. All ligands only act as electron pair donors, or is there a ligand which can also act as an electron pair acceptor? Is there some ligands which can accept electrons from the metal?
CO.
Very good, Suman. CO. Yes or no? So in CO, we will be having the back bonding also, which is also called as synergic bonding. We will be looking that in the upcoming slides.
Yeah, pi bonding, anti bonding.
Yeah, very good. So metal and ligand is there. From the ligand to the metal, the electron pair has been donated. So we lead to the formation of a coordinate bond. But we can also have the scenario, from the metal to the ligand, we can also have back bonding. Okay, from metal to ligand, back donation of electron density is also possible. Back donation of electron density is also possible, leading to the formation of pi bond. So in such cases, we will be having some sigma character as well as pi character with the metal ligand bond. Those ligands which are accepting electrons back from the metal ion, they are called as pi acceptors. Pi acceptor. Pi means why pi? Because the bond formed is pi bond, and why acceptor? Because they are accepting the electrons. These are the basic terminologies. Coordination number, the total number of coordinate bonds formed by the central metal ion with the donor species, that is called as your coordination number of central metal ion. This is simple, right? So how many number of coordinate bonds are formed? That will be equal to your coordination number in that particular complex. The total number of coordinate bonds formed by central metal ion with the donor species. Central metal ion with the donor species, how many coordinate bonds are forming? That is nothing but your coordination number. Generally, coordination number 2, 4, 6 are possible. Coordination sphere. Coordination sphere means it is the non-ionizable part of complex compound. Like if I have K4 FeCN6, the FeCN6 part is present as a complex ion only. It will not further ionize. Yes or no? So in K4 FeCN6, this part FeCN6 is a non-ionizable. This part is non-ionizable, and that is why it is said to be coordination sphere. This terminology is important, students, because the same terminology we are repeatedly using in the upcoming sessions. Yes or no? This FeCN6 part, this is not going to be ionized further. That is why it is said to be your coordination sphere. This part, FeCN6 part. Is that clear? Is everything clear so far? The basic terminologies?
Yes, sir.
Yes, very good.
Yes, sir.
This is your coordination sphere, which is non-ionizable part. The K plus ions is said to be the counter ions. Complex. The classification of complex can be based on type of ligand. On the basis of type of ligand, we can say ligands are of two types, homoleptic and heteroleptic. Name itself we can suggest easily. Homoleptic means the complex having only one type of ligand. K4FeCN6. What is the ligand here? Cn minus. So whenever the complex has only one type of ligand, it is said to be homo. Homo means same, one. Leptic, homoleptic, one type of ligand. Yes or no? The complex can be classified on the basis of type of ligand. Homoleptic complex means the complex having only one type of ligand. Example is K4FeCN6. Heteroleptic ligand, you can say easily. The complex having more than one type of ligands. Example, FeCN taken thrice, NH3 taken thrice. This is just one example. There are a lot of complexes. Yes or no? Heteroleptic ligands or heteroleptic complexes are those complexes where you have more than one type of ligand. Homoleptic complexes are those complexes where you have only one type of ligand. Examples you note down. Heteroleptic complex example is this one. This is just an example. A lot of examples are there. You will see that in the upcoming slides. Right? On the basis of the type of ligands, like how many types of ligands are there, we can classify the complexes into homoleptic and heteroleptic. That is the first classification. Classification of complexes based on the type of ligands. We can also classify on the basis of stability. Perfect complex and imperfect complex. Perfect complex means what? The complex which do not dissociate into constant ions, like K4FeCN6. If you add this to water, what it is going to happen? You get 4K plus and FeCN6 whole minus 4. So this is your complex ion. Yes or no? FeCN6. The FeCN6 4 minus is the complex ion. Is the complex ion. So it is not further dissociating. This K4FeCN6 is dissociating to give K plus and FeCN6 4 minus, but it will not dissociate further. Will not dissociate further. Will not dissociate further. Since it will not dissociate further, it is standing by the original definition of complex. So the complex which do not dissociate into constant ions, that is said to be a perfect complex. Imperfect complex. The complex which gives the test of their constant ions. The complex which gives the test of their constant ions. Perfect means the complex which do not dissociate into constant ions. All of you note it down. Simple definitions. On the basis of the type of ligands, we have classified complexes as homoleptic complexes and heteroleptic complexes. On the basis of stability, we are again classifying complexes like perfect complex and imperfect complex. Perfect complex do not dissociate into constant ions. Imperfect complex, that will give the test of their constant ions. Example note down here in this case. K2CdCN4 upon treatment with H2S, it forms CDS. Cadmium sulfide is obtained. What do you mean by this, students? If cadmium sulfide is obtained, can I say it will give the test of Cd plus 2 and S minus 2? Yes or no? Because cadmium yellow PPT is there, no? In the reaction mixture, if we have cadmium sulfide, we can say Cd plus 2 ions are going to be positively tested. S minus 2 will be positively tested. What about here? Here, this complex upon dissociation gives what type of ions? 2K plus ions and CdCN4 whole minus 2 ions. Look carefully now. This complex is dissociating to give 2K plus and CdCN4 taken 2 minus. This upon treatment with H2S, you are getting cadmium sulfide. What do you mean by that? That means this cadmium, which has been involved with the coordinate bond with the cyanide, is that coordinate bonds disturbed or not? Because cadmium is coming out of this complex ion as Cd plus 2 because cadmium sulfide is formed. Can I say CdCN4 2 minus is undergoing breaking of the coordinate bonds to give Cd plus 2? That means, can I also say indirectly, if these bonds are broken, you are also getting Cn minus ions or not? Cadmium sulfide is present means Cd plus 2 ions are there. Cd plus 2 ions are present means the cadmium come out of that, the cadmium came out of that coordinate bonds. That means if cadmium came out of that coordinate bond, cyanide should also came out of that bond. Yes or no? So if you are two friends are there, very good friends, if one friend comes out of the friendship, automatically the other friend is also out of the friendship. Yes or no? So if cadmium which was interlinked with the cyanide ions by the coordinate bonds, if this is coming out of these coordinate bonds, that means the cyanides are also coming out of the coordinate bonds. So in the solution, what do we have now? K plus, Cd plus 2, Cn minus. So it is giving the test of all the ions or not? You may ask a question, sir, if it is giving a test of all the ions, then why can't you call this as a double salt? Yes, why there any doubt?
No, sir.
No, right? Yes. What I'm saying is, if K2CdCN4, if that is giving the test of all the types of ions like K plus, Cd plus to Cn minus, then why can't we simply call this K2CdCN4 as a double salt? Because it is not giving the ions simply in dissociation with water. We are adding some H2S externally. If K2CdCN4 is simply giving all types of ions, whenever you add that to water, then it is an then it is a double salt instead of imperfect complex. It is giving the constituent cadmium sulfide only in the presence of H2S. So we have added some external agent. So that is why it is a imperfect complex, not a double salt. Got this point, students?
Yes, sir.
Yes, sir.
Yes, very good. So next point, which you can understand is, on the basis of nature of complex ion. Like till now we have discussed on the type of ligands and on the imperfect and perfect complexes. On the basis of nature of complex ion, we can have complex cation and simple anion. These examples. Like if it dissociates, you get CuNH3 taken 4 whole plus 2 plus SO4 minus 2. Complex cation and simple anion. Simple cation and complex anion. K4 FeCN6 use 4K plus and FeCN6. You concentrate on the ions, complex ions. The complex ion can be a cation, it can be anion, and we can have neutral complexes. I have told you in the D block also, with the carbonyl, the D block elements will show zero oxidation states. And we can have complex cations and complex anion like this. So we can have CONH3 taken 6 whole plus 3 plus COCl6 whole minus 3. So we can have complex cation and complex anion. We can have complex anion and simple cation. We can have complex cation and simple anion. We can have neutral complex. So on the basis of nature of complex ion also, we can decide or we can categorize the type of complexes on the basis of ligands, on the basis of stability, on the basis of nature of complex ions. You can just write down the examples: complex cation, simple anion, simple cation, complex anion, neutral complex, complex cation and complex anion. All of you note it down and let me know. If you're done, you can just type letter S in the comment section, or you can just speak out S. Okay, I have no issues with both the sides. Done? Very good. So this is your first classification, students. Then we have to classify the type of ligands on the basis of the ligands. Then we are classifying the ligands. Ligands are classified on the basis of charge, density, and nature of bonding. So on the basis of charge, we can say cationic ligands, anionic ligands, and neutral ligands. On the basis of density, we can say monodentate, bidentate, and polydentate. On the nature of bonding, we can say classical and non-classical ligands. So let us look at one by one. So until now, we have classified central metal ions, and we have classified complexes: homoleptic, heteroleptic, perfect, imperfect, on the basis of type of complex ion. Now we are going to look at the classification of ligands on the basis of charge, density, and nature of bonding. On the basis of charge, how we can say? On the basis of charge, we can have negatively charged ligands, we can have positively charged ligands, and we can also have neutral ligands. Let's first list out the negatively charged ligands and write down this point. For these type of ligands, we use the suffix ato. If we have finally ate, like sulfate is there, means sulfato you have to write. Chloride, chlorido. Sulfite, sulfito. Yes or no? Ate has to be replaced with ato. Ide has to be replaced with ido. Like chloride is there, means chlorido or chloro. Both are same. Both are equal. Chlorido or chloro. Sulfite, sulfito. Nitrite, nitrito. So like that, the suffixes has to be changed. This is a scenario for negatively charged ligands. For negatively charged ligands, we have to replace H with ato. Write down this ligands list. F minus, fluoride, fluorido or fluoro. Cl minus, chloro or chlorido. Br minus, bromo or bromido. I minus, iodido. O2 minus, oxido or oxo. O2 minus, peroxido or peroxo. O2 minus, O2 minus, superoxido or superoxo. OH minus, hydroxido or hydroxo. H minus, hydrido. Write down this, very, very important. Names are important while you are actually writing the IUPAC nomenclature. Studying the IUPAC nomenclature, names are important. F minus, fluoro or fluorido. Cl minus, Br minus, I minus, O2 minus, O2 minus, O2 minus, OH minus, H minus. Right? So all everywhere you have to replace 8 with ato, ide with ido or O, ite with ito. Then we have cationic ligand, students.
Sir, can you show the previous slide?
Note down. If you are done, let me know.
Done, sir.
Done. Similarly, you have to write down the names for the cationic ligands. Here you have to deal with EM, IUM. Nitrosonium, NO plus is nitrosonium or nitrosilium. NO2 plus, nitronium. N2H5 plus, hydrogenium. O2 plus, oxygenium. Write down this. NO plus. Here, if you look at the structures, the nitrogen will be having the lone pair of electron, even though they are positively charged. Since the nitrogen possesses a lone pair of electron, they are going to be acting as ligands. NO plus, NO2 plus, N2H5 plus, O2 plus. Is that done, students?
Yes, sir.
Yes. What Prachi done?
Yes, sir.
Yes. The same thing is repeated. For these type of ligands, we use the suffix IUM. As I have told you, for cationic ligands, we will be using the IUM as suffix. These are the 4 cationic ligands which we have discussed, even in the same slides. And I have also said this point: can ammonium ion act as a ligand? Can ammonium ion, like previously also I have discussed this?
No, sir.
No,
Yes
sir.
or no? No, why? Because it does not have any lone pair. No, it does not act as a ligand, as nitrogen does not have electron pair to donate. Ammonium ion cannot act as a ligand because it do not have a lone pair of electrons to donate. If there is no lone pair, how it can be donating? Yes or no? No, it does not act as a ligand, as nitrogen does not have electron pair to donate. Write down the names of these complex also. These complex ligands. NH3 is amine. Here you have to concentrate carefully. Double M has been used. AMMINE. H2O is aqua. CO is carbonyl. CS is thiocarbonyl. NO is nitrosyl. PPH3, triphenyl phosphine. Triphenyl phosphine, very, very important. Even this is having complexes in organic chemistry. Anyone remember Wittig reaction from the organic
Yes,
chemistry?
sir.
What is that?
Yes, sir. Uh, Sir, hydrogenation of alkynes.
Wittig reaction. Are you sure, Faizan?
Sir, I'm a bit confused
Okay,
between this.
don't worry. So triphenyl phosphine, we are going to be treating with an alkyl halide to generate phosphorus lights. Those phosphorus lights we will be treating with a carbonyl compounds to form a ultimately alkenes are obtained. Yes or no? These are
Yes,
used
sir.
as a
Yes, sir.
yes or no? So the phosphorus lights, phosphorus YLIDS lights. These are generated from this. Phosphorus lights are obtained from PPH3.
Sir, and that one is Wood's reaction in which sodium is used, right?
Yeah, Wood's
Sodium and
reaction is that
alkyl.
one.
Yeah, I am confused between this and that.
Yeah, no, don't need to
Mm.
worry. Wood's reaction is simple. Generation of alkanes by treating alkyl halides with sodium
Sodium,
in the presence of dry ether. And the mechanistic approach for that Wood's reaction is assumed to be a free
free
radical
radical
path.
mechanism.
Yeah, very good. This is completely different, where like we can generate alkenes from this treatment of carbonyl compound with the PPH3 in the presence of alkyl halide and some strong base. Is that noted, students? All the set of neutral ligands. Note down this. We have to apply all this. Okay, the names you should not get confused whenever we are doing the application part. PH3 is phosphine. PPH3 is triphenyl phosphine, NO nitrosyl. CS thiocarbonyl, CO carbonyl, H2O aqua. NH3 is amine, AMMINE. N2H4 is hydrogen. Right? The next set, neutral ligands. O2 dioxin, N2 dinitrogen, CH3NH2 methylamine, NH2CONH2 urea, CH3OCH3 is dimethyl ether. And of course, very less type of complexes we will be studying with these type of ligands, but still they are also having the tendency to donate their electron pairs, ultimately forming the complexes. O2, N2, CH3, NH2, NH2, CO, NH2, CH3, OCH3. These are all the neutral ligands. These are all the neutral ligands. Done? Okay, fine. So next, this is the classification of ligands on the basis of charge, positively charged ligands, negatively charged ligands, as well as neutral ligands. Next, on the basis of denticity. Denticity is total number of lone pairs given by the ligands in the vacant orbitals of central metal atom. Ligands are giving the lone pair, right? Ligands are donating its lone pair to the vacant orbitals of central metal atom. How many such lone pairs are donated? That is nothing but your denticity. So ligands were again classified on the basis of denticity as mono or unidentate, bidentate, as well as polydentate. Let us look at one by one. What is monodentate? What is bidentate? What is polydentate? Monodentate means those ligands which can donate only one lone pair into the vacant orbital of central metal atom. CMA stands for central metal atom. Those ligands which can donate only one lone pair into the vacant orbital of central metal atom is called mono or unidentate. Examples can you give? Simple example: cyanide,
Ammonia, water.
ammonia,
Halogens.
halogens, yes or no? X minus, Cl minus, Br
Water.
minus. Can I say sulfate here?
Sir,
Sulfate.
sulfate is bidentate. Right? It has two O negatives.
S
As
double bond O minus, O minus.
yes. Sir.
Sulfate is actually a flexidentate ligand. It can donate only one electron pair from one of the O minus. It can use both of its O minus. It is categorized as flexidentate ligand. Sulfate is a flexidentate ligand. That is, in some complexes, it acts as monodentate, and in other it behaves as, we will discuss what are those complexes where sulfate is acting. It can behave as bidentate. Right? Monodentate ligands are those ligands which can donate only one lone pair into the vacant orbital of central metal atom. Okay, they can donate only one lone pair into the vacant orbital of central metal atom. What is bidentate?
Can
What is
donate two
bidentate?
lone pair electrons.
Yeah, you can list out. Monodentate ligand means all these ligands. Examples you can note down, students. All below negative, positive, and neutral ligands are examples of monodentate ligands. F minus, Cl minus, Br minus, I minus, NO plus, NO2 plus, Cn minus, Nc minus, Scn minus, NH3, H2O, CO. You don't need to write separately all these. Earlier we have listed the type of ligands, right, on the base of charge. There only we have to mention which is monodentate, which is bidentate itself. There we have not discussed any bidentate ligands. So you can simply write down mono there only. Monodentate ligands are those ligands which donates only one electron pair into the vacant orbital of central metal atom. Bidentate means, as the name itself suggests, which can donate two lone pairs. If we have a bidentate ligand, there is a possibility of formation of a ring or not? Yes or no?
Yes, sir.
Like we have Mn plus.
Yes, sir.
Yeah, we have Mn plus central metal ion. we have a ligand like ethylene diamine, you consider NH2, CH2, CH2, NH2. Ethylene diamine, it has two nitrogens and each nitrogen has lone pair of electron. Because of the presence of lone pair of electron, it is going to be acting as what? Ligand. First of all, it can act as a ligand. And two nitrogens are there. So from both the sides, it can donate. So because of donation of electron pair from the nitrogen to the central metal ion simultaneously from two sides, you are having a ring formation. This is nothing but what, students?
Chelate compound.
Chelate
Chelation.
ligand.
Very good. Chelation. Yes or no? Wherever you have chelation, that is going to be extra stable. Let us discuss those bidentate ligands now. Bidentate ligands are those ligands which donate two lone pairs at a time in the vacant orbital of central metal atom. Those ligands which can donate two lone pairs at a time in the vacant orbital of CMA, that is called as bidentate ligand. It can be, these bidentate ligands are again classified as symmetrical bidentate ligands and unsymmetrical bidentate ligands. What do you mean by symmetrical? Symmetrical are those bidentate ligands having same donor sites. Like earlier I have told, ethylene diamine. Ethylene diamine, write down this. Ethylene diamine is NH2, CH2, CH2, NH2. Lone pair of electrons and nitrogen, they were involved in the coordinate bond formation. Because of that, the metal ion, the NH2, CH2, CH2, NH2, they are forming a ring. What type of ring is formed? A 5-membered ring is obtained. Symmetrical bidentate ligands means the electron donor sites, they are same donor sites. Unsymmetrical means different donor sites. Yes or no? Write down these examples. Example of symmetrical bidentate ligand, ethylene diamine. The process of forming rings by the donation of, by the simultaneous donation of electron pair from two or more than two ligand atoms, two or more than two ligands, two or more than two atoms from the same ligand, two or more than two atoms from the same ligand leads to the process of forming rings by the simultaneous donation of electron pair from two or more than two atoms from the same ligands is called chelation. Okay, this process is called chelation because already ring formation I have written is called chelation. More number of chelation, more the chelation, more is the stability of the complex. What you have to understand, more the chelation, because whenever the ring is formed, the stability gained. Okay, more the chelation, more is the stability of the complex. Stability of the complex. Right? More the chelation, more is the stability of the complex. Then comes another symmetrical binder ligand, acetyl acetonitro. So we have CH3, C double bond O, CH minus, C double bond O, CH3. Yes or no? The oxygens are now donating the electron pairs to the central metal atom. So both the electron donor atoms are same donor sites. So symmetrical. Same donor sites. And what type of ring is formed here? 1, 2, 3, 4, 5, 6. In acetyl acetonitro, we are getting a 6-membered ring formation because that how many rings formed, how many rings are formed, that depends upon the type of ligand. Like if you have a bidentate ligand, it will form one ring. If you have 3 bidentate ligands, each bidentate ligand will form one ring. So 3 will form 3 rings. But what is the how many remembered ring is formed? That will depend upon the type of ligand. Yes or no? So if you take acetyl acetonato, we are getting a 6-membered ring. 1, 2, 3, 4, 5, 6. Is that clear, students? Can I proceed further?
Yes, sir.
Yes, very good.
Yes, sir.
Write down the other example also. DMG, dimethyl glyoxymeto. It should be dimethyl glyoxym, but ato we have to replace 8 with ato. So DMG is dimethyl glyoxymeto, and it can preferentially form complex with nickel. And what is that complex? NiDMG taken twice. What is the oxidation state of nickel here? Nickel will be in the +2 oxidation stage. So DMG should be in which oxidation state? Dimethyl glyoxymeto. That should be in which oxidation state?
-1.
-1. So that -1 is present on the one of the oxygen. So CH3 dimethyl, C double bond N, N connected to OH, N connected to O minus. Nitrogens are donating the electron pairs to the nickel, Ni+2. Similarly, you write down one more, N double bond C, nitrogen connected here with OH, carbon bond, here also N double bond C, carbon connected to methyl, carbon connected to methyl. Here the nitrogen connected is O minus. So this OH bond is there. This is also one more DMG group I have written there. One more DMG group I have written there. So the partial positively charged hydrogen. Why this hydrogen is partial positively charged? Because the OH electron density is moving towards oxygen, generating partial negative charge on oxygen. So the partial positively charged hydrogen attracts with the negatively charged oxygen, leading to the formation of intramolecular hydrogen bonding. Same happens here. Negatively charged oxygen develops attraction with the partial positively charged hydrogen, leading to the formation of intramolecular hydrogen bonding. So this is how you can understand the complex NiDMG taken twice. In this complex, nickel is in which stage? +2 stage. Understood now, students? That means nitrogen has two OH groups, but one of the OH group has lost, and we have nitrogen connected to O minus 1. O minus 1. These are all the symmetrical bidentate ligands. Note down all of you. Very important, this complex are.
Sir, donating electron depend upon negativity.
Sorry, Suman.
So donating power of electron. I mean nitrogen and oxygen. Who will give the electron?
That depends upon electronegativity
depend
and the type of complex form. Yes or no? You ask a question, which is going to be donating the electron easily. So that that depends upon the type of complex form, and that is not just depending upon the whatever the ligand you have taken, and also it depends upon the solution, that is a solvent. Yes or no? Because in a particular solvent, the nucleophilicity changes. So which can act as a better nucleophile, which can donate the electron pair easily, and what type of complex is formed, whether the formed complex is stable or not. Based on all these things only, we have to say which is acting as a ligand or which atom is actually donating the electron pair. We have oxygen also. For sure, we have oxygens. Oxygen also has lone pair of electrons. The lone pair from oxygen can also be donated. If you try to write that, you are getting a chelation complex, whether that complex is stable or not. If it is not random, no, we cannot donate random atoms. We cannot donate the electron pairs from random atoms. If we donate so, we have to look at the stability of the complex formed. If that complex formed is stable, then we can argue. Also, which atom is a better electron pair? That depends upon the electronegativity of the atom. If we have more electronegative atom tend to hold the electrons on itself. Less electronegative atom will try to donate easily. Are you understanding?
Okay, sir.
Okay. Then comes the unsymmetrical bidentate ligands like glycineto. So here we have one electron donating atom is a nitrogen, the other is oxygen. So NH2, CH2, C double bond O minus. Now nitrogen is donating as well as oxygen is donating. Both are now donating now to the central metal ion, M plus. So do we have same donor sites or different donor sites? Different donor sites. Donor sites are different. Donor sites are different. That is why it is a case of unsymmetrical bidentate ligand. Glycinato is the name. Write down this. Glycinato is the name of this particular ligand because nitrogen is donating the electron pair from one side and the other side oxygen is donating the electron pair. And such type of ligand is said to be a unsymmetrical bidentate ligand. And can you list out any polydentate ligands? Bidentate we have seen. Monodentate we have
Ethylene
seen.
diamine. Ethylene
EDTA.
diamine.
EDTA, ethylene diamine. Yes or no? The polydentate, we have more than 2 if donated. Those ligands which donate more than 2 lone pairs at the same time in the vacant orbital of central metal atom, they are said to be polydentate ligands. Examples: diene, diethylene triamine, EDTA is also an example. Ethylene diamine, how we have written? Ethylene CH2, CH2 double bond CH2, we have connected to NH2 groups and replaced the double bond now. We have taken out the double bond. This is nothing but ethylene diamine. Diethylene triamine. Diethylene triamine. So we have 2 ethylene groups, CH2, 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 CH2. These 2 are connected with NH and these 2 are connected with NH2. Now, what type of ring is going to be formed? Now, what type of ring is going to be formed? NH2, CH2, CH2, NH, CH2, CH2, NH2. We can have central metal ion somewhere here. Yes or no? You can have central metal ion somewhere here. To this central metal ion, all the 3 nitrogens are donating the electron pair simultaneously. So how many rings are formed now, students? The charge is neutral. The charge of the complex is neutral and they are neutral ligands. What about density? Density means number of electron pair donor atoms. How many are there? 3. So tridentate. It is 3 tridentate. Number of chelating rings. With one ligand, how many rings are formed? You are getting 2 rings. So write down this formula. Number of chelating rings is equals to density minus 1. Number of chelating rings is equals to density. Density is how much? 1, 2, 3. 3 electron donor atoms are there, minus 1. So 3 minus 1, that will be 2. So 2 rings are formed. So if it is a tridentate ligand, how many rings are formed? With one ligand, 2 rings are formed. If it is a bidentate, you are getting 1 ring. If it is a tetradentate, how many you will get? Tetradentate?
3 rings.
Tetradentate? 3 rings are going to be formed. If it is EDTA, how many rings are going to be formed?
6.
6 rings? Sure?
No,
5.
6 minus 1, 5.
5, no? So ethylene diamine tetraacetate, EDTA is the hexadentate ligand. So 6 minus 1, 5 rings are going to be formed. Because of more number of ring formation, EDTA complexes are stabilized. We look at that EDTA 4 minus. Ethylene, is it noted or not? Note on all of you. Okay, fine. EDTA 4 minus ethylene diamine tetraacetate. Acid 8 has to be replaced by 8O. So acetate. Ethylene. So CH2 double bond CH2. Diamine means both the carbons are now connected with NH2. Ethylene diamine means NH2, CH2, CH2, NH2. But tetraacetate. So all the here we should have 2 hydrogens, 4 hydrogens should be there. All the hydrogens were now replaced with the acetate groups. That is CH2 C double bond O minus groups. CH2 C double bond O minus groups. So since all those were replaced by CH2 C double bond O minus, these are acetate groups. Now if you look carefully, the O minus can also donate the electron pair. The nitrogen can also give the electron pair. So charge, how many C double bond O minus are there? 4 O minus groups are there. So charge is minus 4. So what type of ligand it is? Anionic ligand. What about density? Hexadentate 4 O minus and 2 nitrogens. 4 O minus and 2 nitrogens. Number of chelating rings is equals to density minus 1, that will be equal to 5. What is the number of chelating ring? Density minus 1, that will be is equal to 6 minus 1, that is 5. Is that clear, students? Yes or no?
Yes.
Yes, sir.
Yes, very good. So you will be having ligand means this ligand, if you have, let us say Mn plus is there. So you have a ring like this. Now look at Mn plus, concentrate on this Mn plus. I'll just change the color. Concentrate on this Mn plus, this nitrogen, this CH2, this C double bond O minus. Yes or no? C double bond O minus you can write as C double bond O minus. So we have, what do we have here? Mn plus is there. Mn plus connected to nitrogen. Nitrogen connected to CH2. It is nitrogen connected to another bonds. Those are fine. Look at this one ring. CH2, CH2 connected to C double bond O minus. This O minus connected to Mn plus. So we are getting nitrogen, CH2, C double bond O minus again connected to NH2, Mn plus. This is nothing but one ring. This is nothing but one ring. Similarly, you can have Mn plus connected with nitrogen, nitrogen connected to CH2, C double bond O minus, again one more ring. Like that, you have all the rings, such that how many types of rings are formed? Five rings are formed. Dimple, why charge is 4? So you look at nitrogen connected with CH2, C double bond O minus. So if you look at the molecules, how many oxygens are there with a negative charge? How many oxygens are there with a negative charge? Or is there any atom which has any other charge except the oxygen? Only oxygen is there, right? CH2, C double bond O minus. Only oxygens with a negative charge. These are the charged species. Remaining all are neutral. How many such oxygens are there? 4 oxygens. 4 oxygens are there with negative charge. That is why total charge of -4. So that is why it is anionic in nature. Okay, good. Then comes the informational point. Write down all of you. Very, very important. You will have a doubt. Sir, which type of ion will form how many? Like which type of ion will form what type of complex with what coordination number? There is some rule. Ag plus will form coordination numbers of complexes of coordination number 2. We will discuss complexes of Ag plus even in the metallurgy as well. Cu plus 2, Zn plus 2, Ni plus 2, Pt plus 2. Copper in the plus 2 state, zinc in the plus 2 state, nickel in the plus 2 state, platinum in the plus 2 state. They preferably form coordination number 4 complexes. Fe plus 2, Fe plus 3, Co plus 3, Cr plus 3, platinum in the plus 4 state. They form complexes of coordination number 6. Write down this, very, very important. Fe plus 2, Fe plus 3, cobalt plus 3, chromium plus 3, platinum plus 4. The platinum complexes generally people confuse. Platinum in the plus 2 stage forms coordination number 4 complexes. Platinum in the plus 4 stage forms coordination number 6 complexes. We have to categorizing that. If they have given a complex to you and given some d orbital splitting and all, magnetic data is given to you, then how to figure out what type of complex it is? Is it a plus 2 complex or plus 4 complex? Based on that only we can proceed with the next part of the question. So platinum in the plus 2 state will form coordination number 4. Platinum in the plus 4 state preferentially forms coordination number 6. That means the charges of the central metal ions, they are matrix. Why? Because they depend again upon sizes. So if you remember the concepts of solid state, the radius ratios, they are going to be ultimately determining the coordination numbers or not. The radius ratios. Yes or no? The radius ratios, based on the radius ratio values only, we decide the type of crystal lattice structure. Based on the radius ratios only, we can say whether coordination number is 4, or 6 or 8 or 2? Yes or no? So based on the radius ratio, we are deciding the coordination number. Based on the radius ratio only, we decide the complex or crystal lattice structure formed. Is it noted, students?
Yes, sir.
Yes, sir.
Very good. Oxidation state +1, coordination number will be 2 or 4. Oxidation state +2, coordination number 4 or 6. We look at different types of complexes. First, you should be thorough with the terminologies and all the basic stuff. Oxidation state +1, +2, +3, +4. Oxidation state +3 or +4 means you will have coordination number 6 directly. +2 means you can have 4 or 6. +1 means you can have 2 or 4. Oxidation state +1, coordination number can be 2 or coordination number can be 4. Oxidation state +2 means coordination number 4 or coordination number 6. Oxidation state +3 means coordination number 6. Oxidation state 4 means coordination number 6. This is what I am talking. Flexi-rented ligands, ligands which can change their density. Ligands which can change their density, they are said to be flexi-rented. Example, sulfate I have given earlier. Similarly, CO32 minus, NO32 minus, CH3, C double bond O minus. They are normally monodentate. Normally, they are monodentate only. But in case, in some other complexes, they also have tendency. Like if you look at this complex, here you look at cobalt. Sulfate is in which state? Sulfate is in -2 state. So what is the oxidation state of cobalt? Cobalt is in which oxidation state? 1 cobalt, 1 into X, 5 ammonia, 5 into 0, plus 1 sulfate, 1 into -2 is equals to total charge of this should be +1. X should be +3 or not? Because
Yes,
it will dissociate to give CONH3 taken 5, SO4 whole plus Cl minus. It will dissociate to give CONH3 taken 4, SO4 whole plus 2 plus whole plus Cl minus. Whole plus Cl minus. So what is the oxidation of cobalt here in the second complex? Again same logic, 1 into X plus 4 into 0 plus 1 sulfate 1 into -2 is equal to +1. So X should be is equal to +3. So oxidation state of cobalt is +3 in both the complexes. What do you mean by that? That means in both the complexes, you are having the coordination, you are having the coordination number of 6 or
6.
not? So coordination number 6. So this is also the coordination number 6. This is also having a coordination number of 6. Coordination number 6. But look at the complex now. Cobalt is coordinated with 5 ammonia. And what about other? Other is sulfate. So here in the first complex, sulfate is acting as a monodentate or bidentate?
bidentate.
In the first complex, if sulfur acts as a bidentate, it will form 7 coordinate bonds or not? Already 5 are there from the nitrogens. 5 ammonia are there. From each ammonia, nitrogen is giving the lone pair. So we have how many coordinate bonds? 5 coordinate bonds already there. We need a coordination number of 6. So we should require one more bond. So that one more bond is given by sulfate. So sulfate acts as monodentate or bidentate?
Monodentate.
Monodentate. Write down. So sulfate here O minus, S double bond O minus. So O minus is giving the electron pair. So it is acting as monodentate. In the first complex, SO4 2 minus acts as monodentate. We have to decide this based on the coordination number. Look at the second molecule. Coordination number should be 6. Cobalt is coordinated with how many ammonia? 4 ammonia. and only one sulfate, coordination number should be how much? Coordination number has to be 6, but only one sulfate is there. So in that, in this particular complex, sulfate is acting as a monodentate or a bidentate. Understand this carefully, students. Coordination number 6 means you should have 6 coordinate bonds. 4 coordinate bonds already obtained from nitrogens. So you should have how many more bonds? You should have 2 more bonds.
Bidentate.
So those 2 bonds are obtained from sulfate. So it should be acting as bidentate.
Bidentate.
Okay, acts as bidentate. Fine, students, we'll stop the discussion here. Next class we'll proceed with the different other terminologies, IUPAC nomenclatures, valence bond theories, all those things we'll study. Fine. Thank you all, everyone. Bye-bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.